Hey, welcome to Lab 3, Black Hole and Orbits. So what is the purpose of this lab? This lab's purpose is to calculate the average mass of a black hole by running a computational simulation of the black hole's gravitational pull on a star. And then this is used, the mass of the black hole is used in the second model to calculate the initial velocity of a spaceship and prevent it from crashing while also trying to make a figure-8 orbit. So these observations were done using a computational model including universal gravitation within the GlowScript model. So what are the fundamental principles? First, we have Newton's second law, which is acceleration of an object is dependent on the force, the net force, and the mass of the object. And then uh, Newton's second law is used to calculate the initial velocity using the velocity/position update formula. And then universal gravitation makes up our force. So this is the formula used off to the side: F equals G times m1 times m2 divided by r squared. So what is the system and surroundings in this case? In part one, the system is a star, whereas the surroundings are the black hole. And then in part two, the system is a ship, whereas the surroundings are the moon/the planet. So this is my code. We have the initial momentum is equal to the star's mass times its initial velocity, whereas the final momentum is the star's mass times the final velocity. And then we also have a statement to calculate the mass of the black hole, which is using the magnitude of the net force times the magnitude of the star's position times the magnitude of this star's position again, and then divide that by the g times the star's mass. This is just a rearrangement of the gravitational force equation. And then we also have an arrow scale, which is used to scale our arrows based on our value for the FNet. So the reasoning for this model, as you can see the model on the side, the GlowScript model can generate accurate data for the object's predicted position based on the parallel and perpendicular forces acting on it at that moment in time. So a model also allows for the use of a very small delta t and therefore an accurate calculation of the average mass of the black hole. So what are the results? We get, for the mass of the black hole, we got 5.28 times 10 to the 33 kg. So in the second model, basically we just have an iteration over the net force, and we have four different net forces. So we have the force from the moon, from the planet on the moon, from the ship on the moon, and then from the planet on the ship, and then the moon on the ship. And then basically we calculate the total net force on the moon and then the total net force on the ship. And then experimentally we determine a initial velocity both in the x and y direction that allows us to attempt a figure-8 orbit. So this is my attempt at a figure-8 orbit. We started out with a initial x velocity of 26,000 and initial x speed of 26,000 and a y speed of 27,000, which gave us this. Any other numbers, if I dragged it lower, made it higher, would cause the moon to crash, or the ship to crash into the moon, sorry. So what are some possible sources of error? In part one, incorrect averaging of black hole mass values, and then rounding of the values for each calculations may have caused the error when calculating the average mass of a black hole. Whereas in part two, some errors based on the determination of the black hole mass from model one may have played in. Also, errors finding the FNet and just errors that come about using the trial and error. So what does it mean? Rate of change of momentum versus FNet. So the net force and rate of change of momentum point in different directions. Specifically, the parallel components allow us to analyze the change in the speed of the motion, whereas the perpendicular component relates to the change in direction of the motion. So based on this, we can conclude that the perpendicular forces are equal to each other, whereas the parallel forces are also equal to each other. And rate of change of momentum is the same as the FNet. So what if, the question was, in order to predict the motion of a system using a black hole, a star, a ship, and a planet, a gravitational force would be determined based on every object within the system and within their surroundings. So the dominant force would be the object with the greatest mass, as it contributes to the largest force, which in this case is the black hole, which has a mass greater than everything else. Thank you.